This is a short video segment on chemical bonding and how we represent bonds in the chemistry classroom. This corresponds with chapters 7 and 8 in your textbook. Now, one of the things that's important to remember is that in chemistry, words mean something very specific. We have to be careful when we use words. So when we're talking about symbols in chemistry, we're talking about a non-bonded element in its elementary state. For example, Na is the symbol for sodium, and we can use our periodic table to tell us a whole bunch of information about the element sodium. For example, the periodic table can tell us, the number of protons, neutrons, and electrons. It can tell us that sodium has similar properties to the elements lithium and potassium. And last unit we used it to determine the electron configuration, which told us how many electrons were involved in bonding. Sodium having its last electron in the 1s energy level indicates that it will bond using just one valence electron. Now, when we say formulas, we're talking about bonded elements. You can see here from the examples, I'm using the formula NaCl to stand for the compound sodium chloride, and the symbol CO, or the formula CO2 to stand for the compound carbon dioxide. And this is what this unit is all about. The first thing we're going to do is talk about what's the difference between those two types of compounds in terms of how they're bonded, how do we represent them using a particular Lewis electron dot structure, which is just one model of bonding. We're going to talk about how we can determine their properties, and then from that, how do we know how to name those compounds? How do I know that that is sodium chloride and carbon dioxide? What are the rules for nomenclature? And then in the next unit, we're going to talk about equations, and you can see an equation is for a chemical or physical process that's occurring. Liquid sodium reacting with gaseous chlorine to form solid sodium chloride. So when I say write the formula for it, it's very important that you don't give me an equation. Or if I say write the equation for, it's important that you don't give me a formula. Your book does something I don't like, and when they're writing formulas in chapter 7 and 8, they use a yield sign, or they use that arrow, and I think that that's confusing. They should just leave that out. So just be careful. We're going to use arrows to indicate that a chemical process has occurred or that a physical process has occurred, not that two things have bonded. Okay, so the first thing to consider are what we can learn about ionic compounds. First of all, you should pay attention and note that ionic compounds, for our purposes, will always start with a metal atom, and those are located on the left-hand side of the periodic table, or they might have a positive polyatomic ion. We're going to talk about polyatomic ions later. We call an ionic compound a formula unit. You've probably heard the word molecule before, but molecule is used specifically for covalently bonded compounds. So how are they bonded? This is when an electron is transferred from generally the metal to the nonmetal, because we know that metals will have lower electronegativity values than nonmetals will. Those electrons will transfer. And when that electron transfer occurs, then we have ions. And those ions are attracted to each other due to their oppositely charged particles. The structure for an ionic compound, in your book went into detail about crystalline structures. I really just want you to know that it's a crystal, that it has a particular shape, that crystal is a very set crystal. It's a very rigid arrangement. The properties of ionic compounds, they're solid at room temperature. So if you have an ionic compound, and I haven't told you what the physical state is, you should know that it's a solid unless it's been dissolved in water. They have high melting points and boiling points. That's what leads them to have the solid state at room temperature. And they're usually water soluble. There are some that are not, and there are some that are only slightly soluble, but they generally are pretty soluble in water. And they are electrolytic when they're molten or aqueous. You may have heard the word electrolytic before. I know that it's very popular to drink sports drinks today, and they have electrolytes. By the way, most people don't need to drink those. But anyway, they they have these ions floating around them to keep our heart beating. Our heart works on an electrical impulse. Without enough ions dissolved in our blood, the heart will stop beating. So the word molten means melted. Think of your molten chocolate cake. That's melted chocolate. And aqueous, of course, means dissolved in water. So in their solid state, in their crystalline state, they will not conduct electricity. And the strength of an ionic compound depends on its lattice energy. We'll talk more about that later, but what we're going to use is something called charge product. Later on, you'll learn that the charge of a calcium ion is positive 2, and the charge of a chloride ion is negative 1. And if we multiply 2 times negative 1, thus charge product means multiply, we get the value 2. And that would indicate that calcium chloride is pretty soluble. So the lower the charge product, the weaker the lattice structure, and the more soluble the compound is. Covalent compounds, for our purposes, they're going to start with a nonmetal on the periodic table. Remember, there aren't many nonmetals on the periodic table, so we're going to have many fewer covalent compounds in this class. This is an inorganic chemistry class, so we're not looking at lots of carbons bonded to each other. In terms of compounds that exist in the world or in the universe, there's many, many more covalently bonded compounds than there are ionically bonded compounds. We call a covalent compound a molecule. H2O is a molecule of water, whereas NaCl is a formula unit of sodium chloride. They're bonded by sharing electrons, and we're going to learn how we can predict their structure or their shape based on something called valence shell electron pair repulsion theory. And as we start doing models for that, you'll be able to get a look at what those particular shapes are. We have a whole lab on it. Properties of covalent compounds, they have low melting points. That means that they're that they're liquid or gas at room temperature. And they are volatile. You might think that that word volatile means something really exciting, like explosive. And that is not true. Volatile just means that it evaporates at room temperature. That perfume you're wearing, that Axe body spray you boys are putting on, that is a volatile organic compound, also called a VOC. You may have heard of those in paint or in cars, the new car smell. It's not good stuff to breathe. And they're volatile because the forces of attraction that hold them together are relatively weak. And covalent compounds are also non-electrolytic. They will not conduct electricity. The strength depends on something we call bond energy, and we'll talk a little bit about that, but bond energy is the energy needed to break the bond. And that is something that is easily measured in an advanced laboratory, certainly not in a laboratory like this, but at universities and companies where they have advanced labs, they measure bond energy. Those have been recorded and put in books for us to look at when we want to. Okay, so the compound formula tells us some things about the substance. SO3 tells us that there's the types of elements that are in the compound. It tells us there's sulfur and there's oxygen. It also tells us the relative quantity of the two. When I say relative, that's comparative. There's 3 oxygen atoms for every 1 sulfur atoms. And it also tells us the way the compound is bonded. Since sulfur trioxide, SO3, starts with sulfur, which is a nonmetal, that tells us that this compound is covalent. And because we know that it's bonded by sharing electrons, we also know some of the properties of sulfur trioxide. It's a gas at room temperature, it's non-electrolytic, it's volatile. Volatile really is only if it's a liquid at room temperature. But that will tell us the properties of that compound. So this next question is a really good question to ask. Which of the following compounds are oh, I think I'm missing something. Oh, electrolytic. So what is that really asking us? I'm asking you about a property, but this isn't a very hard question. If you know that electrolytic is a property of ionic compounds, then this question is really asking us, hey, which one of these compounds are ionic and which are not? So we're going going to look at the first element, and if the first element is a metal, then we know that it is electrolytic, because that would indicate an ionic compound. If the first element is a nonmetal, it is not electrolytic. So looking at your periodic table, take a minute to find sodium in family 1. You can see that sodium is a metal, and therefore this compound is ionic, and we would predict that this is electrolytic. SCl4, that'd be sulfur tetrachloride. Sulfur is element number 16 on your periodic table. You can clearly see that that is a nonmetal, and therefore this compound is covalent. Oops, and therefore not electrolytic. Aluminum oxide. Aluminum is element number 13 on your periodic table. Get a look at it. You can see that that is to the left of the stair-step line, and therefore it is a metal, and that compound is ionic, which would be electrolytic. Potassium is element number 19. That is a metal, so that compound's ionic and therefore electrolytic. F2 is fluorine bonded to fluorine. That would be covalent, so that would be non-electrolytic. And then oxygen, element number 8, is a nonmetal, and therefore that compound would also not be electrolytic. I'll probably quiz you on something like that. Next question, which are volatile? Well, if volatility is a property of covalent compounds, this is really just asking us which ones are covalent, so then that would leave us with the ones that we indicated were not ionic. Because a compound is either ionic or covalent. There's nothing in between. Wow. For you. Okay, so why do bonds form? What happens is the electrons of one atom become attracted to the nucleus of another, and as they pass by each other, that creates this kind of uncomfortable force. And by allowing the electrons to approach the other nucleus, it actually lowers the potential energy of the process. So we're allowing them to get close, we're allowing them to attract to each other, and therefore lowering any potential energy. Remember that potential energy is just unused energy. And if there's a separation between positive and negative, there's unused energy. I want you to think on that one. And then there is the octet rule. We know that octopuses, octopi, have 8 legs, right? Octet means 8. The octet rule says that elements that have 8 valence electrons, that would be having their S sublevel and their P sublevels full, will have greater stability than elements that do not have 8 valence electrons. So really the whole thing is that bonding occurs just so that these elements can fill their octets, can fill their S and P sublevels. It's convenient for us that we have all these nice compounds, but there's really only one reason it happens, and that is the octet rule. That here's the trap. And we know that they can occur in 2 ways: electron transfer or sharing of electrons. We just went over that. So how do we determine bond polarity? Bond polarity is another way of determining the character of the bond. Is the character of the bond ionic, meaning the electrons are probably shifted and transferred from one atom to another, or is it covalent? And there's three types of bonds that can occur. We can have nonpolar covalent bonds. Nonpolar, meaning the electrons are shared equally. Covalent, meaning the electrons are shared. So here we have shared electrons, and the electrons are shared equally. Polar covalent bonds, covalent, electrons are shared, and with a polar covalent bond, they're shared unequally. It's as if you and your sibling share a car, and your sibling is a bully and doesn't ever let you drive the car. Well, that would create a polar covalent sharing situation. And remember that last unit we discovered electronegativity as the attraction for electrons. So if we're sharing these electrons, the element with a greater electronegativity is going to have the electrons more frequently. And then, if the electronegativity values are so different, then we get an ionic bond. So the electrons are transferred from one atom to another. Here's some pictures to help you out. A nonpolar covalent bond, this blue cloud is kind of showing the electron clouds and how the electron density is even dispersed. Black dots are the nucleus. And then you can see for the polar covalent bond, the electrons are shifted in this direction towards this element here, making this one have a partial negative charge and a partial positive. It's not a true negative or a true positive like an ion is, but it does have a moment where it is negatively charged. That's why we call it a dipole moment. And then the ionic bond is showing the transfer of the electrons, where the electron cloud for the positive ion gets smaller, the electron cloud for the negative ion gets bigger. Okay, to determine bond polarity or bond character, we're simply going to use this chart of electronegativities, and all we're going to do is subtract, and then we're going to compare it to this scale that's at the bottom. This is posted on the website. You may print one for your convenience, or I will, you've got one that you can use while you're in class, and then you can just look at this, the ones online if you need to, but print it if you want, it's here for you. So if we want to know the characteristics of of a compound that is bonded when sulfur and hydrogen bond to each other, we're just going to look at the electronegativity value for sulfur, 2.5. I don't remember what it was. Was it oxygen? Hydrogen. Now we're going to look at the electronegativity value for hydrogen, 2.1. And we're simply going to subtract 2.5 minus 2.1 is 0.4. If we look at the scale, 0.4, or anywhere between 0.4 and 1.68, is a polar covalent bond. So we would say that this is polar covalent. Oops. And the element that's going to have a greater share of the electrons is going to be the sulfur. It has a higher value of electronegativity at 2.5, whereas the hydrogen is 2.1. So the electron cloud is bigger for the sulfur, smaller for the hydrogen. Okay, why don't you take a minute and do these three. I'm just going to pause this here. Okay, so hopefully you've taken a minute to answer those questions. And you can see by subtracting the electronegativity values, we can predict that a compound has ionic or covalent character. We have two ionic compounds and one polar covalent compound, where the electron density is shifted towards the oxygen. So we see that with bromine and oxygen's electron cloud is going to be bigger, bromine's is going to be smaller. With cesium and chlorine, it's easy to see that chlorine is going to take the electrons. So chlorine is the one that's going to form the negative ion. Cesium is going to lose electrons, so it's going to form a positive ion. The same thing with calcium and chlorine. Chlorine having the greater electronegativity, it's going to form the negative ion, whereas calcium will form a positive ion. It happens to be a positive too, but we'll talk more about that in a minute. Okay, so there's a quick introduction to bonding. The next video segment is going to be on how do we draw dot structures.